In this video, we're going to go over esterification and saponification. Saponification will carry us on to the next page, but we'll start with esters. Esterification, if you remember, we did a lab on this, or I shouldn't say this, you will do a lab on this right after this. So this is going to be really good notes to have because this is exactly what you're going to be doing in the lab. So esterification is what it sounds like. You're making something into an ester. Esters typically smell nice, but they don't always have to, but they do typically have smell. Whether you consider it good or bad is a personal preference. So the way you make a ester is by adding an organic acid and an alcohol and mixing them together. Now, you haven't learned this about acids, but acids like to give off their H pluses. They give off NH plus is a better way of saying it. And specifically, and again, we will learn this, that in an organic acid, the H attached to the OH, the part that looks like an alcohol, that H is going to come off, okay, as an H plus. And that H is actually going to react with the alcohol from the alcohol, and that is going to come off to make water, because when you add an H and an OH together, you make water. Now, that leaves this carbon with not enough bonds, and it leaves this oxygen with not enough bonds. So what happens is the oxygen and the carbon bond together, and that is, that's this bond right here. I'll use yellow because it's a little bit better. So that's this bond right there. All right, and that's how it works. So for these two practice problems, you're going to do the same thing. The H and the OH come off and make water, and then we take what's left over and link them together. Now, if you happen to get it wrong and you accidentally did the OH from the alcohol and the H from the, or the OH from the organic acid and the H from the alcohol, it's ultimately not going to make a difference. But if they ask you to circle which ones come off, if it were a Regents question, I have seen this, and they said circle the ones that are going to come off to make the bond, then you need to circle the H from the organic acid and the OH from the alcohol. But if it was just draw the products, then they're not going to know. And even if you circled them on the Regents and you happen to get it wrong, like if you accidentally circled the wrong pair, if that wasn't part of the question, I don't think anyone would care either. I personally wouldn't, because I'm only going to look at the answer. So what do we get? And so those are your esters. The hard part about esters is going to be naming them, although that's not in this lesson. You should know how to name them already, but drawing it out is really not that bad. You just have to know this is what happens, and I have actually seen this question show up on Regents. Saponification. Well, everyone says it's saponification. I like to say soaponification, and the reason is because saponification is making soap. So when you make soap, it's pretty easy. You take a fat, you add a base, which is, again, a chemical that we haven't learned about yet, but it's similar to an acid. So you've probably heard of the word base as acids and bases. So you've definitely heard of that. So we take a fat, we add a base, we get a glycerol. Again, you don't need to know what that is. It just looks like this. And then we make a soap. So the way the easiest way to identify saponification is it uses this big, giant E-shaped molecule. And if you look, it's even bigger because see the CH2 with a 6 outside? That means there's 6 repeating CH2s along this chain. And then you make this even bigger molecule where you pretty much take them all and lump them together and you get this giant chain, okay? And that's what saponification is. You would never have to draw this. But you may have to answer questions about like which reaction is saponification and what makes a soap a good soap. And that actually leads us to our next topic. So not our next topic, but our continuation of this one. So down up here, I have draw a soap molecule. So to draw a soap molecule out, let's take a look. We start with a CH3, and then it's going to need 16 CH2s. Then it gets an O, an O, and I don't even have space, an Na plus in brackets at the end. Normally this thing is put in brackets like that. okay? So that's your soap molecule. I am not writing out all the hydrogens for this. I'm just going to put the lines. Okay, and the reason the soap molecule is so gigantic is because of two things. There's a saying that we like to use, and you're going to learn more about this, but it's called like dissolves like. And it's used with the saying that you already know, SNAP, symmetrical, nonpolar, asymmetrical, polar. And what it means is this: polar molecules like to dissolve in other polar molecules. This is actually the answer to why oil and water don't dissolve. Polar molecules like to dissolve in other polar molecules. Nonpolar molecules like to dissolve in nonpolar molecules. We will explain the whys when we get to the actual unit where we learn this officially. I'm just kind of giving you a brief introduction. And the reason oil and water don't dissolve is because water's polar and oil's not. All right, and so if you ever look at salad dressing with like the layering, that's why they never dissolve into each other, and they always end up separating, is because they have different polarities. Well, what makes a good soap is that it washes off everything. It'll take off oils, it'll take off water-based stains. So normally you don't really need a soap to clean off something that's soluble in water, even though we use it anyway. But soap, what makes a good soap is that it can do everything. It can dissolve polar things because it has a polar end. It can dissolve non-polar things because it has a non-polar end. And the question would be, well, how would a molecule be both polar and non-polar, right? It's usually you're asymmetrical and you're polar, or you're symmetrical and you're non-polar, right? That's normally the way it works. Well, there's a different issue going on with the soap molecule. The soap molecule is so long, it would be like if you had a house that was so outrageously big that someone could be over here having a house party, right? And you could be all the way on this end of the house and not even know what was going on because the other end is just so ridiculously far away. Now, most people don't have that scenario, but that's what happens in a soap. On this end of the molecule, if we look, it is symmetrical and therefore nonpolar, okay? And then this end of the molecule is so far away from the other side that it almost resets the symmetry. And now we can actually do it again on this end. And if you look, you could say, well, in this case, with this double bonded O and this O and Na on this side, this end is asymmetrical and therefore polar. And because the molecule is so long, it can actually do both at the same time. And that's what makes something a good soap. If you get something that's oil-based on you, right, like oil, like you're cooking and you get grease on you or something like that, well, this end of the soap molecule is going to take care of that and try to dissolve it. If you get something that's salt-based or water-based on you, well, this end of the molecule is going to be able to dissolve that. So that is what makes something a very good soap.